Cummings. I'm a professional geologist and I work for Holdridge & Cole. I have 16 years as a consulting geologist now. It seems like I just graduated not that long ago. But 16 years have gone by really fast, and let's see, I've been with Holdridge & Cole for the last 5 years, and then with various other firms all the time before that. And when I started out with an internship at the Department of Water Resources. So still, I think, a friend of the department here. Let's see, this project is actively under construction right now. So this is something that I am deeply involved in every single day. I get phone calls from the contractor, the client, the water board. So it's very intense schedule. But today's the 8th, and we're here to talk about all of the various aspects of it, from the preliminary work that I did all the way through the design of the perimeter dewatering trench that I worked on with Don Olson, who's he is the principal engineer for the project, and then worked with Jeff Cox to get him all the pictures, and he came out with a what the heck is that thing called? The flying drone camera, and he took pictures of the trenches and the excavation and the entire site, and he came up with a really cool overview video that I'll show you guys. But anyway, it's the Closed Lincoln Landfill, and it's a corrective action dewatering cutoff trench. So the highlights are the video overview, which is really a pretty cool thing. I'm going to go over the background of the project, the site geology and the hydrogeology, nature of the contaminant release that's emanating out from beneath the landfill. Then we'll talk about the perimeter dewatering trench system design, and then go into the construction. Got a lot of cool pictures. I think I counted today there was something like 1,157 pictures. My engineer's been doing a great job. And then the challenges that we had. We had a number of different things that we didn't anticipate encountering out there. So we had to overcome those in order to meet the project schedule. And then what's next? Even though we're almost done with construction, now you've got the system in place. What do you do with it now? So let's go back to the movie and check that thing out.
I'm with Holdridge & Cole. I'm an engineer and a geologist. We're at the Closed Lincoln Landfill site. This is a landfill that operated from the early 1900s till about the mid-1940s, maybe the 50s, as a burn dump, where they would come out and excavate a trench, put the waste materials, just typical household waste in, and then light it on fire, and then backfill it with soil. And there's approximately 5 to 6 trenches out here that were operated that way. And then the site was closed, and later on in the 70s and 80s, they were looking at all these old burn dumps and finding out that groundwater was moving into them and out of them and carrying contaminants off-site. And that was found in monitoring wells. Since then, the California Water Quality Control Board has asked for sites like this to be cleaned up, and sometimes that means clean closure. We'll excavate all the waste material out and haul it off to a licensed landfill site. Sometimes it has to go to a hazardous waste site, and sometimes just to a regular Class 3 municipal solid waste site, such as where we're hauling ours to, which is Austin Road Landfill in Wheatland, which is about maybe 15 miles from here. So what we ended up doing was, after doing a characterization of the site, we designed a dewatering system. And the dewatering system, rather than using conventional wells to pump the groundwater out, we used a trench system. And what the water board had mandated was that the water table had to be lowered to a minimum of at least 5 feet below the bottommost elevation of the waste. So we designed a trench system around the perimeter of the site, and the site encompasses about 6 acres, and it's a relatively flat site in pretty much a square shape. And then that water within the landfill would move into our trenches, which are filled with gravel, and then the flow of that material, or that effluent, would then move to the sump locations, which were constructed at the corners of the trenches, and then it's then pumped out and into the sanitary sewer. So here is the landfill, this square area here, and these are the trenches where the burn dump waste goes at. So the trench that we're putting in runs around the perimeter like this, and then is pumped out into a pressure pipe system that then discharges into the sanitary sewer. Now, if you look at this drawing over here, you'll see a cross-section through showing where the waste materials are at. These are two different cross-sections showing basically the same thing. The regional water table being up here, up in the waste, the 5-foot separation depth here minimum that they have to achieve, and then this is the trench on the side, one side, this is a trench on the other side, and this is the configuration of where the water table will be drawn down to in order to achieve that minimum 5 foot. And actually we've designed it so we'll have a factor of safety so that we'll have like a 10-foot separation. If you go over to this drawing here, this shows again the trenches in the center of the landfill and the perimeter dewatering trench, as well as the corners showing where the sumps are at, and then a piping system that will take from those sumps and discharge all the water into a manifold, which goes to this outer piping system that will take it to the sanitary sewer. Now this over here, this drawing shows the cross sections on the alignment of each of the dewatering trenches. So what is significant here is that we have at some locations as deep as 45 feet that we have to excavate a 3-foot wide trench. In other areas it can be as shallow as 20 to 25 feet. And the material here is then removed and then replaced with a crushed rock, and then the bottom is graded to drain to each of these corners, which would be shown on this drawing that I had showed you before, and then pumped out. So it's really actually a fairly simple project. We have had some challenges with because they're deep trenches of some caving issues. So we've had to come up with some solutions during the construction process to mitigate that. But by and large, it's been a pretty smooth going project. It's rather simple. We're just trying to get the water out of the landfill to draw the water level down at least 5 feet below the bottom of the waste. And in the process, we'll also be pulling water in from outside of the landfill where some of the contaminant plume has traveled to. So we'll be actually extracting that, coming back into the landfill, and then all of this is disposed of at the city sanitary sewer system. So that's pretty much what the project is, and we'll take you out and show you some of the construction actually ongoing in the field.
That kind of gives a good overview of what the project design is. And any questions that you came up with from seeing
Looks
that?
pretty easy and simple to do.
I know, just build a 3-foot wide trench, no big deal.
I have a quick question.
Yeah, go ahead.
What type of assurance do you have to have that the water table isn't going to change, or is the trench just going to really efficiently disperse that water table away and it won't allow any rise?
There's we had quite a bit of data on the hydrogeology there at the site. Specifically, there was slug test data to give us hydraulic conductivity. We know that our groundwater table fluctuates, pretty about 10 feet semi-annually, or depending on much rain we get. We also know that we have very, very low permeability soils. So we had quite a bit of information. The slug test data was considered to be somewhat unreliable in terms of the wide range of hydraulic conductivity we had. So if you plug in the highest hydraulic conductivity into the equations that we used to figure out how deep the trenches are, we came up with some wide-ranging discharges, and we may not achieve 5 feet of separation across the entire site. We may not achieve it in the middle, which would be the most likely place that we wouldn't. So there's not really any assurances, and you can never give your client, this is the golden egg that's going to fix your problem, but you can certainly use the data that you have to come up with, you know, your best estimated guess at it.
Okay.
But we'll go over some more of the design stuff here. That's a great question. So this is the location. The city of Lincoln, you know, is outside of Rockland and Sacramento, just to the northwest. Our site is here on the corner of Hungary Hollow and Virginia Town Road, and the Auburn Ravine runs along there. To the south of the site, it's not very far away, in that you can see the tree line there, so the creek is just right there. It's an unlined Class 3 landfill at 6.3 acres, and it's roughly square in nature. It operated from 1952 to 1972, and they disposed, you know, the municipal waste and green waste in these trenches that they dug out, and then caught it all on fire, put some soil on top at the end of the day, did it all again the next day. They burned the waste in order to increase their fill capacity. So unlike at Neal Road landfill, your fill capacity is limited by how well you can compact that solid waste and what you can divert from the waste stream. And then in 1993, they finally put an official prescriptive cover on it, which is 2 feet of cover soil, which is typically the native material that you have there on site, and then a 1 foot clay cap, and then a 2 foot or 1 foot vegetative layer. And that is, the prescriptive cover is defined in the regulations on the solid waste regulations on what that's supposed to look like. You can do other things. You know, at Neal Road landfill and other more modern facilities, they put a geosynthetic liner on top of the clay in order to really keep that water out from infiltrating into the top.
For context, Chico had one of these.
Yeah.
And not that far from here, right up Bruce and Highway 32.
Yeah.
And I don't know if you, did they deal with that in similar ways, or do you know?
Yeah, so they have a prescriptive cap, but they also have the geosynthetic liner on that one. The primary wastes are very similar to this site, where it's lead and arsenic, and then just whatever's in the trash that they haven't really identified. But that's it, because it was uncovered for so long, and they're kind of right in a drainage. They had a lot of migration of lead and arsenic out into that drainage, which they just did another remediation out there when they put in that new culvert for the new the housing out there.
Oh.
So they did a removal action there for the arsenic and lead out of that drainage. So the site is regulated by under waste discharge requirements, and those are stipulated in Title 27. It's the solid waste regulations. And the Regional Water Quality Control Board is the lead agency for this facility. They underwent a long history of trying to get the corrective action system in place. In February of 2000, the Regional Board requested that they do a corrective action. They had a number of issues getting adequate monitoring wells placed around the facility in order to fully characterize the off-site contaminant plume that was emanating from the waste itself. In September 2003, they adopted new waste discharge requirements, which required them to fully characterize that groundwater plume and required them to maintain their 5 feet of separation. 5 feet of separation is for all landfills, whether they were pre-existing or they're brand new design and we're going to put them in tomorrow. And then 10 plus years passed before they got all their monitoring wells in, and the water board was kind of miffed And they said, well, guess what? You get a cleanup and abatement order. And with a cleanup and abatement order comes a lot more, it's much more serious. You are subject to civil liability. And there's a few different water code sections that give the water board the authority to levy fines for entities that don't comply with their cleanup and abatement order and their waste discharge requirements. Those two on top there are in the water code, and then California Code of Regulations, Title 27. Division 2 is the solid waste, and that's where it defines, what your design standards are for new and existing solid waste landfills. And like I said, potential fines are $10,000 per violation per day. So if you don't meet the requirement, it becomes very expensive very quickly. And this remedy that we proposed was one of several that were looked at in the corrective action plan. They did an engineering feasibility study, another consulting firm, and this one was one of the alternatives that they looked at, and was actually the least expensive alternative. At the end of the day, when they submitted their corrective action work plan, they wanted to close the site, which was a $14 million to $20 million price tag. The city went, oh my goodness, we don't have that kind of money. And so they came to us and asked us to just do a peer review to make sure that they were on the right track. And so we did that, and it was about a $5,000 effort. You have to get up to speed on all the different characteristics of the landfill, the groundwater quality of the geology, make sure that, you're basically looking at somebody else's work and making sure there's no data gaps that could result in one interpretation over the other, and therefore selecting one remedy over another. So we did find some data gaps in that review, and came up with a plan to just verify that the geology was in fact what they had indicated was in the report. There was some conflicting information in there that in the logs, in the geologic logs, that suggested they may have a granitic style aquifer instead of a sedimentary aquifer underneath the site, which could lead to potentially a situation where you have confined groundwater and your pressure head is coming up in your wells, and if you just draw a line across that pressure head, it looks like you have water in your waste. But if you have a confined system, it's really not in your waste, it's just down in the rock, and it's pushing up because of the pressure head that it's under. And we thought, well, maybe we've got perched groundwater on top that's just hanging out in the bottom of those trenches because they're like big bathtubs filled with less permeable material, so the water's going to move in there. So we went out and we drilled 4 piezometers around our site just to make sure that the geology was what we hoped it would be. And then, well, if it had been a granitic site with a confined system, we wouldn't even have to go down the corrective action pathway, other than to maybe pull back some groundwater that's moving off site. But with the geology being a sedimentary unit, which is the riverbank formation, we knew then that the groundwater was in fact coming up into the waste periodically, and as it would fall, then it would drag those contaminants and dissolve salts down with it, and then migrate off site as groundwater naturally does. So like I said, it's the riverbank formation, it's the middle unit of the riverbank formation, it's Pleistocene age, it's 2.6 million years old, and it looks like decomposed granite. You go there and it's got nice quartz crystals, it's got the biotite, the muscovites, and then the silts and clay-sized particles. It's very, very tight formation. It's weathered and reddish gravel, sand, silt. And like I said, we confirmed the geology with the data gap investigation. We actually installed dual nested piezometers where you can monitor the groundwater in the shallower zone within that 5-foot zone of separation, and then in the deeper zone to see if there's any vertical gradient differences. On that's our site, on the geologic map. The site hydrogeology, at the time when we did our investigation, there were 17 groundwater monitoring wells. There's a series that are guard wells out, or background wells that are up gradient of the site. These were the original up gradient wells right here. But they realized that they were really close to these waste trenches that run across here. These are the waste trenches here. And we've got offsite wells around here and perimeter wells here to monitor the plume and what's going on out here. And then one over there. So the groundwater, it flows generally to the southwest. Sometimes it kind of just mounds away from it because this is sort of a natural mound in the topography. Auburn Ravine is down here. This well down here, MW17, is not in the riverbank formation. It's in the recent alluvial sediments. So anything that's migrating off in this direction, we're never going to see it in this well because the hydraulic conductivity is orders of magnitude faster than the rest of the site. And then every once in a while, the groundwater flows back towards the site from the Auburn Ravine as the water levels rise and fall in there. So groundwater is 13 to 22 feet below the ground surface, pretty much generally across the site. You know, our hydraulic conductivity, like I said, it ranges significantly from 1.64 times 10 to the minus 8 to 2.56 times 10 to the minus 6, which would be at this well, and then pretty much any of these, number 18, which was an offsite well, had the very lowest hydraulic conductivity. The gradient ranges from 0.016 to 0.08. That's pretty typical for groundwater gradients. It's not too steep and pretty average. And our seepage velocity using our low hydraulic conductivity is 1.7 feet per year. And then if you use the high one, it becomes 365 feet or so per year. So this groundwater down here is scooting along pretty quick relative to the groundwater on the site. For southern flow direction. This are cross sections. So here's our site. We did 4 different cross sections. I selected the 2 cross sections that are in the deepest trenches, so you can see, you know, when groundwater is at its highest elevation, you've got it entering the bottoms of those trenches. And how do we know where those trenches are? There's been a series of borings that came down. They pretty much put a grid on the site and just drilled across the entire place with a geoprober to determine where the wastes actually were. So yeah, you get pretty much all of the trenches. A, B, C, D, and F prime are trenches that get groundwater that comes up into them, and then it commingles there with the waste and dissolves the salts, and then the salts, you know, travel down into the regional groundwater. This is essentially what our groundwater plume looks like. This is an ISO concentration contour map. You can see that it's sort of focused here on these 2 monitoring wells at 2,000 parts per million total dissolved solids. I believe their tolerance limit for background is somewhere around 200, so they're much, much higher than the background concentrations. The plume extends offsite about 300 feet towards MW18. I flipped the map on you guys so that north is now that way instead of up. So MW18 is up here in the corner, and the Auburn Ravine is on that side. In addition to the total dissolved solids plume, we do have a few volatile organic compounds that are detected. Primarily in this far corner, we do have some consistent detections of 1,1-DC and PC, which are related to solvents that we used in dry cleaning applications. There are some other detections of VOCs, but we can safely say that they're probably anthropogenic in nature, probably from the sampling or the laboratory procedures. Let's see. And like I said, there's no changes in the background at MW17 because that groundwater velocity is so high right there. So the idea with the trench too, not only are we going to get the 5 feet of separation, but we're going to we're gonna be extracting this groundwater plume and sending it off to the wastewater treatment facility. We'll get the plume from the inside, and then we'll start to capture some of the outside waters as well with the trench. So, on to the design. This is our site. It's about 500 feet long on a side. We've got the deepest corner here is a 50-foot deep sump structure, which is essentially a monitoring well, but we decided to call them sump structures because then we don't need monitoring well permits for these things. One less fee to pay. So the trenches come along the edges here. They're about 5 feet off the fence line.
Is north back up again?
Yeah. North up one.
Yes, sorry.
Okay.
Thank you. Yes, I think from here on out, north will be up. That's what happens when you use multiple consultants in the past. So yeah, the deep one is up here. We've got the trenches. They have a hinge line in the center here where this portion will flow that direction, and then this portion will flow to the south, and similarly on all these edges. We have a monitoring well that it's actually been installed right here. It's just not on this map, and that's our well to help us identify whether we're achieving that 5 feet of separation across the entire site. We've got a manifold here that brings all the discharge piping, which we run around the perimeter, that comes together here, and then it will exit off the site. And this sanitary sewer is about 1,000 feet down the roadway, and we are able to discharge there without any real restrictions other than occasional monthly sampling for just GEOS. Some structures are going to be fitted. We haven't yet installed them yet, but they're going to have these pressure transducers that'll operate the pumps. It'll tell the pump when to turn on and tell the pump when to turn off, so it's pretty much a self-automated system. And then it also will talk to somebody's cell phone, hopefully not mine, on the cellular network to tell us if water levels are rising above where we want them to be, or if the pumps stop working or something happens. So we talked about the manifold. There is a shut-off valve there just in case we need to do system maintenance. There's at each of the substructures we have also a flow meter and totalizer and sampling ports at each sump structure, and a sampling port on the combined flow, so we know what we're getting to the wastewater treatment plant. But if for whatever reason, because our flows are going to be really low out of this thing, we show up to do our monitoring and it's actually not pumping any water at the time, we can just go and turn each pump on individually and capture the sample that way. That way we're ensuring that, you know, we're giving the data to the wastewater treatment plant that they need in order to comply with their waste discharge requirements. Yeah, that's that. Oh yeah, I forgot about these animations. One of the things we did do on the conveyance piping and the electrical conduit was we rerouted it. Instead of going through here, we had it come up this way because there was a big dip in the topography, so it was much easier for the contractor to move it this way, and then we don't have to worry about pipe getting vapor lock because it's got dips and sways in it. It's just one straight continuous run uphill. All right.
Did you have to worry about keeping the dust down during this whole thing?
Yes.
I know they did that at the Chico burn.
Yeah, so because our facility was already closed, we didn't have the concerns where we would be exposing people to lead contaminated soils or arsenic contaminated soils, except when we actually did encounter waste in our trench, our trench that we dug. But the entire time you have to use dust control measures is essentially just applying water liberally across the site. Not enough to run off, though, however. So in the design, the big question was how deep do they need to be in order to achieve 5 feet of separation? And then is the site boundary close enough? Too far? You know, if you have a 500-foot run and that's what your constraint is, can you live with that? So Here, again, we're showing the water table intersecting trench F prime, I believe that is. So we estimated the maximum height of the water table above the impermeable boundary. Boundary is, so this is one of the wild assumptions that we made to kind of estimate this. But when I found out about the equation that we used, which is a closed form analytical solution by Dupuy, and what we found out is that this distance didn't really affect the outcome very much. It was highly dependent on how much infiltration you get and your hydraulic conductivity. So we were comfortable with letting this kind of float up and down as we needed to. Of course, again, the constraints, the site boundaries, which, you know, are you okay with a 500-foot long trench and nothing in between? Are you going to be able to capture that water down the center of the landfill as well as the edges? The trenches, the waste trenches themselves, you know, if you can avoid having to dig through them, that's always good, because it keeps the costs down. You don't have to take as much material off-site, and you don't have as many health and safety issues to deal with. And then the low permeability soils. You know, there was one of the alternatives evaluated in the feasibility study was a pump and treat system, and because of the low permeable soils, the pump and treat system, each well, your well spacing would have to be very, very tight. You know, you have a well here and another one 10 feet away. So that became very costly to install. So we chose this, and all the literature that we looked at supported the trenching for low permeability soils over the extraction well system.
Heidi, how come, you touched on this briefly, but was it not feasible to put a east-west running trench through somewhere in the middle of the field between
Between the trenches? We didn't really look at that as an option when we figured out that our trench spacing was going to be adequate. Certainly, we considered, okay, well, what if in the future it doesn't dewater in the middle? So we can either put in, you know, 3 extraction wells and then connect it to the existing system, discharge system, or we could dig another trench, or we could horizontally drill as well. That was another alternative that we kind of looked at, but it would just come down to, you know, is this working or not?
Yeah.
So, yeah, we can. Yeah. Oh, and the infiltration, that was a big question in the beginning, because there has been some settlement that's occurred across the landfill cap, and there's been some repairs that have been made where they had big, long, linear cracks in the vegetative soil cover on the top. So they came back in and they repaired that surface, but we don't know what the integrity of the clay is underneath. When we have years and years of drought conditions, you know, how desiccated is that material under there, and is it cracking and allowing infiltration from rainwater, you know, landing on the surface of the landfill? If that's the case, if we have high infiltration, this system is probably not going to work very well. So there is our 5 feet of separation boundary that we need to achieve, but because there was quite a bit of uncertainty in the information that we did have, we decided, well, let's take it down to 10 feet below the waist, and that'll give us some leeway, hopefully some breathing room to let this system operate as we need it to. So like I said, we use the Dupuy theory of unconfined flow to cut off trenches, and then after we did our corrective action plan, we got a comment back saying, well, how do you know that your trench spacing is right? So I went out and looked up some more information, and this Hoogout's 1940 steady state drain spacing formula is used for determining just that, how far, what's that distance. It actually gives you what this distance is here. So again, hydraulic conductivity, a big factor. If your hydraulic conductivity is much, much higher than what you think, then your drain spacing is going to be too far. So our estimated time to dewater is 3 years. Ta-da! We just did a real simple calculation. We said, all right, we got 3 gallons per minute coming out of it, and then we have about 4.3 million gallons. So how many years is that going to take to dewater it with a porosity of 25%? And we'll see.
Could the drought speed that up though? If you go into a prolonged drought and you have
Yeah,
the
and
regional
if
water
we have,
table drops?
if the water level continues to stay low, then yes, but,
We can hope.
I'm sorry?
We can hope.
One giant light.
Heidi, are you counting on no water coming in?
Yeah, so basically, because you don't have the information about the integrity of the cap, you have to say, all right, we're gonna assume that the cap is functioning as intended. And then if we encounter the situation where the system isn't dewatering, then we have to look at other things like how well is the cap performing, and do we need to, at that point, repair it, or do we just need to install another trench down the center of the site? But that would be considered optimization of the system. Let's move on to construction. This is the fun part with all the pictures. Okay, so we installed 2,000 lineal feet of dewatering trench around the perimeter, buried in depth from 15 to 50 feet. And so inside the trench, our intention was to line the trenches with a woven geotextile fabric, which will keep the fine materials moving into the crushed rock and keep that hydraulic conductivity wide open, those pore spaces wide open, and then it'll just move the water freely down to the sumps. But we had a number of situations where we weren't able to install the geotextile fabric, and we weren't even able to install we had a pipe down in the bottom of the trench too, like a drain pipe, so it's like a giant French drain system. But we'll get to the challenges here in a second. So, okay, yeah, so the geotextile filter fabric and the 4-inch perforated HDPE pipe. Pipe is more of kind of a bells and whistles thing, because the gravel is going to move that material whether the pipe's there or not. All right, so we placed the sump casings and vaults. We thought that these guys would go out and place all the crushed rock and then come back with a drill rig and drill down through the crushed rock and then put these casings in. They dug a giant 50-foot hole, which we were not anticipating. So again, the discharge piping, 2,000 lineal feet. We have 2,000 lineal feet of electrical conduit that's running along the surface, so the pumps will be down inside those casings, and then we'll pump the water to the surface and then out through the discharge piping, and then out to the sanitary sewer, and this is the clean out that we tied into. So we installed a power pole. It took 6 power poles for PG&E to come down Hungry Hollow Road to get to our site for our 4 little pumps that we need to run. We installed the new monitoring well, and we extended the riser casings on these 2 wells that are shown here. They were flush to the ground, so this will just make it easier for people to get to when it's time to come back and monitor. We only had 50 working days, which was a big challenge for us. So the contractor really had to know what they were doing and be on top of everything that needed to happen for the site. During the course of construction in that top photo, we encountered waste materials that are actually extending off-site. And during our discovery of that, we learned that the fence line is actually not on the site boundary. It's on their property. So our trench is on their property.
Whose property?
On the neighbors.
Friendly neighbor?
Fortunately, yes. But anyway, we didn't really go and disclose that openly, but
Till now. It's on tape.
Turn the camera off.
but it is what it is, and it is off-site. The fence line, I think, was marking the boundaries of the waste, and we ended up digging through this portion of on the southwest corner, or southeast corner rather, where materials are definitely have moved off-site and are buried off-site. So we continued and dug and installed our trench, and we have access from the adjacent property owner to go over there and clean that material out, and then do some confirmation sampling, and the water board will bless it, and it'll be clean closed on their side fence. So we had a number of trench wall cave-ins. This especially in the deeper portions, so we had just such low soil moisture, the walls just failed. So we came up with a new alternative method of trenching. We benched down 10 feet, and it was like 8 or 10 feet wide, and then we dug the 3-foot trench on top of that bench down to the depth that we needed it to. So that was designed on the fly. You guys got to see some actual footage of the caving, which is pretty scary when you're standing there and this big, huge cavern just goes. And then we were right up against the road on those big cave-ins too, so there was some concern about protecting the roadway. And then we had to cross the roadway to get to our sewer cleanout, and we got phone calls from the public to the Public Works Director, my client, saying, why am I having to wait here for so long? But it was more like 5 minutes, and I think they were just ready to go home and eat dinner. And then, like I said, well, the clay cap had some deficiencies on the back slope of the southern slope of the site, so the contractor brought in some additional clay material and made that the 1-foot thick clay cap that we needed. So the next steps, we'll just continue out our construction project. I believe they are going to complete on the 14th, which means that the pumps are up and running. Their equipment's pretty much off-site. The final BMPs for stormwater protection are installed. All the final site grading is completed because they are kind of smoothing out the bumps and things of the settlement areas. Everything's got to be done on the 14th. So then, you know, that just, you generate the punch list, they go through that and get it all cleaned up, and everybody's off-site. And then we generate a corrective action installation report. That was supposed to be due on October 1st. We just got an extension for October 31st. Woohoo! And then we'll take over from the contractor the stormwater pollution prevention, inspection and maintenance of the facility for at least through January 30th, so until the site is stabilized, which in this case will be 70% of the vegetation has to be back to where it once was. System startup and monitoring. Once that system starts up, we have a short frequency or a higher frequency of monitoring that occurs where we collect samples on a weekly basis. We go out there daily initially, and then weekly, and then we go to monthly monitoring after that. And that'll take us out through January 31st. And then after that, we are technically done with our existing contract. And then the future will be long-term operation and maintenance and optimization in perpetuity, forever. I believe that is it. And then Nate gets a cameo. So that was my class. It was field camp, Anza Borrego. It was a wild and crazy bunch. Any questions? Go ahead.
I had a question about the instrument that you used to figure out how deep the original trenches were that had the garbage in them.
Oh.
Was it just like coring? And you took a core?
That was a confirmation of some geophysical data that was generated by the previous consultant. So they went out and ran, I want to say, about 6 geophysical lines, and they were able to determine from those really how deep, how wide, and then they also did a magnetic survey, and then they did a refraction survey, I believe, and they could, you know, tell the difference in velocities of the material where the bottom was. And then once they kind of knew where those boundaries were, they went out with the geoprobing and confirmed what they thought they saw in the geophysical.
Was it a shortcoming there that led you to dig through trash for your trenches?
No, we knew we were probably going to encounter it. Yeah. So we had a contingency plan in place for when we did encounter it, to sample the material for whatever the receiving landfill wanted us to sample it for, and then take it to them. Yeah. Yeah.
Does the water that you're collecting, is that contaminated with the lead, arsenic, and
No.
solvents?
No.
And why not?
Um,
Isn't it percolating through the trash and then into your trenches?
Yeah, so why not is a good question. I don't think that there's that much, well, I don't know for sure, because we only have 3 borings with actual lead and arsenic and heavy metals data for the entire facility. So how much lead there really is, and when they did those samples, they took the total lead concentrations and they also ran it for the soluble threshold limit concentration, which gives you an indication of how soluble the lead is, and then of course how well it's going to reach out into that water. So the concentrations that we had were really, I think our STLC limit for hazardous waste in water is 5 milligrams per liter, and we were at 3 and 8 for 2 of the samples. So there's not, at least in those locations, there's not a lot of lead to be had for leaching.
Are you monitoring for that?
Yeah, they do monitor annually, I believe, for the metals constituents.
So then you think the trenches are intercepting groundwater before it gets to the landfill material? Do you think that's why it's not contaminated? Because the trenches are catching it before it goes through the landfill?
No.
No.
Oh, our trenches, I see what you're
Yeah,
saying.
yeah. The trenches.
Yeah, that's ultimately what we would like to see happen. The trenches are really there to just lower that groundwater table. The TDS, although it's above background levels, is not really a primary concern for the water board. But the lead and the other metals there, they're just not very soluble in water. And then, yeah, our trenches will capture whatever leaches out at the bottom of that landfill. Everything's not really.
But after 3 years, it should go back to having just
Yeah,
outside.
eventually
Yeah.
it should just be clean water again. Yeah.
Do you know how much of a drill down we need to catch the outside food? What's the going out of the?
No, we didn't evaluate the outside effects. There are closed form analytical models that can do that, but I didn't have the time or the budget to go down that pathway. So we just focused on that inside, which was what the water board said, you make 5 feet of separation. So it's okay, let's do that. It is a good question.
Is this a up and coming trend around California to deal with these old burn sites? Or is that gonna see more of these types of projects coming in the future? Or is this not, is this an anomaly?
No, this one is kind of a legacy thing for the city of Lincoln. They, like I said, they initially got their order to do a corrective action in 2000, and then in 2003 they really said, you really need to go do the corrective action. By 2013 they finally got offsite access to put the monitoring wells in, and it just sort of dragged on because of the access issues, and then the water board said, this has gone on far too long. But there are the legacy sites all over the state of California, but most of them are regulated similarly, and they may not have that groundwater issue coming up into, like, I don't think, I think at the time that they closed this, they knew that they might have a groundwater issue because they did excavate one of the trenches to generate and backfill with clean soil to generate that 5 feet of separation at the time. But we had a lot more rain in the interim that brought the water level up even higher. So then it was in fact intercepting the bottom of those trenches.
Is there, on the regulation side, since you bring that up, have you noticed in your career a change? Are legislators thinking about longer term climate cycles when thinking about mediation and groundwater, and still just the prescriptive things are keeping
Yeah.
moving through?
I mean, I haven't seen it in the landfill design, but we haven't, Holdridge & Cole hasn't done a landfill design in a very long time, so I'm not close to that in terms of landfill design. I know on the construction side for, development of cities, there's lots of opportunities for looking at not so much climate change, but how to better keep the water cleaner for longer. Drainage swales, bioswales, lots of new technologies coming around for the stormwater side of things in terms of construction. That's a hard one to know.